Welcome to Digital Electronics Lecture Series. I, Professor Hitesh Dholakia, is going to explain you R-2R ladder digital to analog converter in this video, and here I'll be explaining R-2R ladder digital to analog converter with voltage switched type of network, right? And in my next video I'll be making current switched type of R-2R ladder DAC. So here let us see the circuit first, and then I'll discuss all the basics which is there regarding this circuit. So here in R-2R ladder digital to analog converter, we are using operational amplifier, and in this here we are taking output, and this is inverting terminal and this is non-inverting terminal. We are grounding non-inverting terminal, and from inverting terminal we'll be having feedback resistance. Let us say feedback resistance is RF, and over here I'll be having R-2R ladder network. So you see here with R-2R ladder network in parallel I'll be connecting 2R resistance, and in series I'll be connecting resistance R. So here I'll be making 3 bits R-2R ladder network. So for that I need to connect 2R resistance in series, and 4 at last I need to connect extra 2R resistance like this, and this extra 2R resistance that I need to ground over here, and with this 3 resistance of 2R I'll be connecting digital switch, where you'll be finding this digital switch that we are connecting with reference voltage. So here if I say my reference voltage, let us say that is minus V reference voltage. I'm adjusting this reference voltage to minus the reference voltage. The reason is I wanted to have positive output. If you take only V reference as it is mentioned in some books, then you will be finding your output voltage will be negative, right? So there is nothing wrong in consideration of minus reference voltage over here. And as I have told you, here there are 3 digital switch that I'm going to connect. So here you see this digital switch that we are connecting like this, where if it is 1, in that case it will be connected to reference. If it is 0, then it will be connected to ground. And this is 3 bit, so this is A3. One more digital switch that I'm connecting, and this is A2. One more digital switch that I'm connecting, and that is A1. Now see here this digital switch which is A1, which we consider as MSB, and this A3 that we need to consider as LSB over here. Now there are a few important points that one should understand. So let me explain you that once, and then we will prove it one by one. So here as you can observe, we are only using R and 2R resistors, right? So when you want to fabricate this digital to analog converter, at that time it will be easier for fabrication. Why? The reason is only 2 resistors are there. If you see my previous video based on binary weightage digital to analog converter, in that we have been having 2R, 4R, 8R, 16R, 32R. That is how we have been having different resistors, right? But here with R-2R ladder digital to analog converter, we have only 2 resistors, R and 2R. So it will be easier for fabrication over here. Now in second point, we need to understand this network, where you will be finding even though you have many number of bits, resistance of this entire network, that will be remain same, right? And you'll be finding that resistance will be R. So we can say we can easily scale number of bits over here without managing many resistors, right? As we have seen it for binary weightage resistor. So here easier scaling that is possible even though more number of bits are there. So as if you want to increase number of bits, then all you need to do is you need to connect one more series resistor and one more parallel resistor as it is there over here, right? So we can easily scale this network with respect to number of bits. And third and most important point, that is to have output impedance of this network is R regardless of number of bits, right? So here even if you increase number of bits, this network resistance that will not change, right? So that network resistance will remain R only. It is not depending on number of bits. So I'll explain you how this impedance network is R, right? And to have this, let us draw this network over here. So I'm just drawing this network again. So I'm just considering this much amount of network, and let us calculate impedance of this network. So you see these two resistance that is in parallel. So equivalent resistance of these two parallel resistor, that will be 2R parallel R, which will be R, right? So equivalent of this parallel resistor 2R parallel 2R, so that has to be R. So I need to connect R resistance in series with this R. So you will be finding now solved version of this, that will be R in series with R. Now you see these two are in series. So R plus R, that will be 2R. And now you again see this 2R that is there in parallel with this 2R. So this 2R parallel 2R, so that is again making this resistance to R, and that is again in series with this R. So you see this R and R again, that is in series, so that will make resultant is 2R. So this 2R again, it is parallel to 2R, so that will make this resistance equivalent to R. So as I have said, impedance of this network is R regardless of number of bits, right? So even if you increase number of bits, this impedance of this network, that will not change, it will stay as R, right? Now what we will be doing is, we will try to identify what will be my output voltage as if I press switch A1 and I'll make A3 and A2 equals to 0, right? And after that I'll check it for A2, and after that we will check it for A3, right? So as if A1 is 1, A2 and A3 is 0, then we need to see what is our output voltage. So as I have told you, if A1 is 1, then with this A1 we are just connecting V reference voltage, and with A2 and A3 it is 0, means we are connecting it with ground, right? Now we need to identify what is our output voltage V0. So you see we need to solve this 2R parallel 2R, so that will make this R again R in series with R, it will be 2R parallel 2R, so that will be again R, and R in series with R, so that will be again 2R. So here you will be finding this circuit, that will be now based on this circuit we need to identify what is our output. So here in this circuit we need to identify what is our VTH, right? So in this circuit VTH, that will be voltage over here, right? And that we can identify as per voltage divider rule. So this V reference, right, that will get divided in between 2R and 2R. So you'll be finding now VTH, that will be minus V reference into 2R divided by 2R plus 2R. So that has to be minus V reference by 2. So VTH voltage, that is minus V reference by 2, and if you observe these two resistance are in parallel, so 2R and 2R parallel will be R. So Thevenin's equivalent resistance RTH, that is 2R parallel 2R, so that has to be R, right? So as per this, again we can redraw this much amount of structure, right? So we can say, now you see here we have RTH, that is R. Here we have minus V reference by 2, that is our VTH, and that is what we are connecting, as you can see, right? So as per this, now my output voltage, that I can say V0 is equals to minus RF by R into V minus V reference by 2. So that is RF by R into V reference by 2, right? So here we can say if A1 switch is 1, in that case RF by R into V reference by 2, that is my output voltage, right? Now let us check this thing for A2 is equals to 1 and A1 and A3, that is equals to 0. So for that again I need to draw this circuit. So let me do that. So as if A2 is equals to 1, right, then this is where we are connecting minus V reference, and this is A1 and this is A3, which is 0, means we are connecting it with ground. Now we need to identify what is our output voltage. So for that, first I need to solve this circuit. So you see this is what 2R parallel 2R, so that is R, and that is in series with this R. So R series with R, that is 2R. So now I need to redraw this structure again. So that is, you see here we have 2R resistance, here we have minus V reference, and this is 2R, and again I am drawing this circuit again. Now see, to identify output voltage, again for this much amount of circuit I need to calculate equivalent Thevenin's resistance. So equivalent Thevenin's resistance, that will be 2R parallel 2R, that is R for this much amount of circuit, and equivalent Thevenin's voltage at this terminal, that will be minus V reference into 2R divided by 2R plus 2R, right? So that is minus V reference by 2. So at this terminal, let us say this is node A. So at A, VTH, that is minus V reference into 2R divided by 2R plus 2R, so that is minus V reference by 2, and RTH, that is 2R parallel 2R, so that is R. So again we need to redraw this circuit. So here you see I am having VTH, that is minus V reference by 2. This is my resistance R, which is RTH, right? And that is what at this terminal, which is terminal A. Now that is in series with R, and I am just redrawing this structure again. So now again you can see this is what R in series with R, so that is 2R, right? And to simplify this network, again I need to consider this node, that is node B. So see, at B again we need to find VTH. So VTH, that is this voltage, that is minus V reference by 2 into 2R, right? This volt resistance divided by equivalent of this R series with R, that is 2R plus 2R. So that will be minus V reference by 4. And if you calculate RTH, so RTH is 2R parallel 2R. So that is R only. So as per this, at this terminal B, if I redraw this Thevenin's equivalent, then here Thevenin's equivalent voltage, that is minus V reference by 4. This is RTH, that is R, and this is what my terminal B, right? And that is what I am connecting it with non-inverting terminal, and here we have feedback resistance RF. So now based on this we can have output voltage, so V0. Now you can clearly observe that is minus RF by R into minus V reference by 4. So we can say this is RF by R into V reference by 4. Now similarly, as if you check this for A3 is equals to 1 and A1 is equals to A2 is equals to 0, in that case you will be finding your output voltage V0, that has to be RF by R into V reference by 8, right? Now as per this we can be able to write generalized equation which is there with this R-2R ladder network, right? So generalized equation we can say that is V0 is equals to, you see, RF by R, that is common in all, right? And into V reference, that is even common. Now you see, we can say A1 by 2 plus A2 by 4 plus A3 by 8. See, this is how generalized equation that we can write. And here we have considered reference voltage, that is negative reference voltage. So resultant output, that is positive, right? Now based on this we can identify analog output, right? So if you write table of digital data, so digital data, that is A1, A2, A3, and our analog output, that is V0, then you will be finding there are total 8 combinations. 1. Now as per this formula you will be finding it will be 0 at 0, 0, 0, and it will be, now you see here if I further simplify this, where if I say RF by R, that is equals to 1, then I can say this will be V reference into A1 by 2 plus A2 by 4 plus A3 by 8. And now if I place A1, A2, A3 in this equation, then our output voltage at 0, 0, 1, it will be V reference by 8. At 0, 1, 0, it will be 2V reference by 8. So this is how we have digital data and analog output relation, right? And see, this circuit that is quite better compared to binary weightage digital to analog converter, as we just have two values of resistance connection in this circuit, right? While if you observe that previous circuit, then there were many resistance, and I hope that now it is clear to all of you like how this R-2R ladder that is useful. And now in next video I'll explain you one example based on R-2R digital to analog converter, which will resolve your understanding further.